Today we discuss the exponential function f of x equals e to the x, but before we do, I want to talk about some background on general exponential functions. Generally, exponential functions are of the form f of x equals a to the x. And here, this is base a. We know that a must be positive and it cannot be equal to 1. And then we have some really important properties that come up working with these functions. We have a to the 0 is 1. We have a to the x, a to the y. This would be a to the x plus y. And then if we have a power to a power, we multiply. And then if we have 1 over a to the x, this is a to the minus x. Now, okay, probably every single one of these we have already used this semester, but they're quite important, these properties of exponential functions. Now, what do these look like? Well, there's really two basic shapes. We just discussed, or at least mentioned, every exponential function satisfies a to the 0 is 1. This means it goes to the point 0, 1. And then one basic shape is if the base a is bigger than 1. It looks like this. This is exponential growth. And then if the base is between 0 and 1, it looks like this. Exponential decay. What's important about the number e? Well, let me just mention e is approximately 2.71828, and this goes on forever. It's an irrational number. It's kind of like pi in that sense. And your book defines the number e in this section in terms of something called power series, and defines e to the x in terms of power series, which is accurate. But this is really something that I wait until Calc 2 when you really study power series. And so I'm going to take a little bit different of a treatment. So how can we get E? Well, as A varies, this curve varies. And I'm going to show you in Desmos in just a moment some moving graphs as I vary A. Okay, so this curve looks different for different A. And E is the special number. It's the only base, such that the slope of the tangent line to f of x equals e to the x at x equals 0 is 1. Okay? So E is the special number that the slope of the tangent line here at x equals 0 is 1. Now let's look at this graphically and try and understand this statement. In black, this is the graph of f of x is 2 to the x. And you see if I increase it to, for instance, here's 3. This is f of x is 3 to the x. And both of these are exponential growth. I could keep increasing the base. Here's 5. This is the graph of f of x is 5 to the x. Okay, they all, with base bigger than 1, have a very similar shape. It's exponential growth. Now, if I make the base less than 1, okay, something like this. This is an example of decay. This is 0.9 to the x. And similarly, the closer or the smaller the base gets, closer to 0, but still positive, we see more steeply
decreasing. Well, but I want to talk about this notion of the special number e. It is the value or the number so that f of x is e to the x. The slope of the tangent line at x equals 0 is 1. And so if I click here, now we can see the tangent line graphed together with the function. And I can, oh, maybe I'll hit play. Okay, you see how just changing a, well now a is going all the way up to 10, but you see varying a, this tangent line changes in steepness. And now it's going back down. Okay. Okay, let me stop this for a moment. So if you might remember this when you first learned about slopes of lines, you can count over and up and get an estimate of the slope. Definitely here, if we count boxes about over 1, it's up more than 1. So this line has slope bigger than 1. But if I decrease, this 2.9 looks pretty close to 1. If you see here where this cursor is pointing, let me get a spotlight here, and then count 1, 2, 1, 2. It's pretty close to 1. Okay, so just by looking at this graph, it seems E would be close to 2.9. And if I change it here, that also looks close to, we have over 2, up 2. That green line is very close to slope 1. And similarly, so, but if I go too far down, now this slope is clearly less than 1. So there's only 1, right? Because as I change A, the tangent line changes, the slope changes. There's only one value such that this green tangent line, which we are watching move with the picture, has slope exactly 1. And it's the closest I can get here. Now, it would be y is x plus 1. That would be exactly the tangent line to e to the x at x equals 0. And we can tell if we go far away, let me zoom in some. I love Desmos very much. You can tell these lines aren't exact, right? So E is not 2.8, but it's close to it. We can tell that by looking at the two tangent lines.
And this is what we were just discussing. E is the number, it's the only base such that f of x is e to the x, has instantaneous rate of change at x equals 0 equal to 1. So what does this mean? What do we get immediately from this? Immediately we see, if you take a limit as h approaches 0 of, let's see, e to the h plus 0 minus e to the 0 over h, that this limit is 1. And if I simplify this slightly, e to the h plus 0, I'll say, or this is just e to the h, e to the h, e to the 0, well, any base to the 0 is 1, so we get this. This equals 1. Now, just knowing this and some of the properties of exponents that I have erased, we can immediately get the derivative of e to the x. Here we go. Now, generally, if we want f prime of x, this is a limit as h approaches 0, e to the x plus h minus e to the x over h. This is the limit definition. Now, let's do this in a few steps. This is a sum up inside the exponent. And so this I may write as e to the x, e to the h, minus e to the x over h. And now you see e to the x has no h in it. So I have it in both of these. I can not only factor it out of the numerator, but I can pull it outside of the limit because there's no h. So this would be e to the x times the limit as h approaches 0, e to the h minus 1 over h. And this limit is 1. It's how we've selected e. And so we get here. So the derivative of e to the x is e to the x. And I used this a few videos ago. I think it was the product rule day because I wanted to differentiate something. And I just told you this was the derivative. But now is the day to do more examples. The derivative of e to the x is e to the x. And this should be your favorite function to differentiate because it's the only function such that the derivative is itself. Well, okay, and also multiplying by a constant. But the derivative of e to the x is e to the x. Okay, wonderful. Now let's do some examples. Here are our first 2 examples. This one will be a little shorter, well, I think, because it's just a sum of terms, and we differentiate term by term. Okay, so when we find y prime, derivative of this, well, we write down the 3 and then differentiate e to the x. So the derivative of 3e to the x is 3e to the x, and then derivative of a constant, 0. When we go to differentiate, maybe I'll write it. Okay, you don't have to write the 0. When we go to differentiate this term, this is a 5x to the minus 3. Okay, so we bring down the power. This would be minus 15x to the minus 4. So we have 3e to the x minus 15 over x to the 4th power, although this is perfectly fine. Now, here you see quotient rule, okay? When we find y prime, denominator times derivative of the numerator and the derivative of e to the x, minus the numerator times, well, this is x to the 1/2 power, so derivative of the denominator is like this, and then all over denominator squared. And I'll leave it like this, okay? Here are 2 more examples. The first is a sum of 2 terms. We will differentiate term by term. This is just a single term. It's e to a function, e to the x squared plus x cubed plus 7. That's all up inside the exponent. And maybe I will start with this one. This is chain rule. One place we want to look for an inside function is up inside of an exponent. So the inside function is x squared plus x cubed plus 7. Okay, and the outside function is e to the x. So then when I perform chain rule here, the derivative of the outside function, that's just e to the x. So we have e to the, well, normally I'd put a big parentheses and put the entire inside function. Okay, then multiply by the derivative of the inside function, which is 2x plus 3x squared. Now you don't need these parentheses here. We could just write it like this. Either one is perfectly fine. Okay, here, as I mentioned, this is a sum of 2 terms, and this first term is a product, and it's very similar to one we did on the product rule day. So when I differentiate, I have first times derivative of the second plus the second times derivative of the first. This part was product rule. And now let's differentiate this, the 7e to the 2x. Well, the 7 comes along, but this is one reason I did this one first, up inside the exponent of e, that's an inside function. So to differentiate e to the 2x, it's a chain rule. Okay, the derivative of the outside evaluated at the inside times derivative of the inside function. Okay, so this would be the derivative, well, in each case here. Here are two more, and then I will do an example that is more than just calculate the derivative, but chain rule, and well, we have some choices here. Let's start with the first one, chain rule. We see the inside function, e to the x plus 6x, and the outside function is x to the 3/2. So y prime here is, bring down the power, big parentheses, power minus 1, and then I put the entire inside function, okay? Then multiply by derivative of the inside function, which is e to the x plus 6, chain rule. Now, let's see, I'll probably do this one as a chain rule, so let me rewrite it, e to the 1 over x plus 8 to the minus 1 power, and we still want to find y prime, okay? But I will have two different chain rules here, as we will see. So the first chain rule, the inside function is e to the 1 over x plus 8, and the outside function is x to the minus 1. So minus 1, big parentheses, to the minus 2. Inside, I put this, okay? And now multiply by the derivative of the inside function. Well, the derivative of 8, that's 0. Here, the derivative is another chain rule. So I will have derivative of the outside evaluated at the inside, and then times derivative of the inside function. Okay? This is a really great example that comes to us from the land of probability and statistics. This function, well, its graph is this famous bell curve for a standard normal distribution. In this standard part, it means that the mean is 0 and that the standard deviation is 1. So perhaps you have heard of the normal distribution in a statistics class before, but we want to find the inflection points, okay? Now, inflection points, these are the points, say x values, where the concavity switches. And any problem that is asking something about concavity or inflection points, we know this has to do with the second derivative. So maybe first in this space, I will just calculate the first derivative. And I really only need that here as a step towards the second derivative. Okay. Well, this is just a number, 1 over square root 2 pi. This is the function part, and we see e, and then raised to an inside function. So this is a chain rule. The first derivative is, well, the 1 over square root 2 pi comes along, and then we have derivative of the outside evaluated at the inside, and then times, well, the derivative of the inside function is minus x, okay? Now this is the first derivative, and as I mentioned, it's just a step to calculating what I'm really going to be working with in this problem, which is the second derivative. So now I look at this function, and how do I differentiate this? Well, fundamentally, I see a product. Let's see. Here's my first, and then times, and then here is my second. Okay? Product rule. So I have the first times, well, the derivative of the second, -1, and then plus the second times, well, the derivative of the first, and we could differentiate again, but you notice the first function here, which is underlined in purple, is the same thing as my original function, right? So we have the derivative already in a sense, but I could also just do a chain rule again. We have derivative of the outside evaluated at the inside times derivative of the inside function. Now, what do we know about inflection points? The second derivative must be 0 or does not exist. Well, they're points in the domain of the function where the second derivative is 0 or does not exist. And then there's more to that. We actually have to check that it switches from concave up to concave down or concave down to concave up. So the first thing I need to do is, well, I'm going to want to simplify this sum because I have to set it to 0. So let's see, we can factor out a 1 over square root 2 pi from both terms. We can factor out a e to the minus x squared over 2 from both terms. And then I'm left with negative 1 plus x squared. This is the second derivative. This is defined everywhere. And so the possible inflection points are where this is 0. Now this looks complicated, but it's really not too bad to set to 0 because this is a number, never 0. This is e to something, never 0. It's always positive. And so I really just need to look at where this is 0. And this is x squared is 1 or x is 1 and minus 1. Okay, but we're not finished. We wouldn't just answer this and be done because there's work to be shown. We must check that the concavity switches. So here's negative 1, 1, and I can write the intervals minus infinity to minus 1 to 1, and 1 to infinity. This would be, if I was specifically asked for intervals of concave up and concave down, I would divide the domain just like this. Pick an x value in each interval. Let's say negative 2, 0, 2. And we want to test the second derivative. Okay. So we make a chart. And then the second derivative is like this. This is the second derivative. And then I'm using 2, 0, minus 2. I'm kind of running out of space here, but I think we can fit. I just need pluses and minuses. This is a positive number. E to a power is always positive. Now this at 2 is positive, at 0 is negative, and at minus 2 is positive. And so my second derivative goes plus, minus, plus. If I add this information to my number line, I have, where should I put it? I have plus, minus, and then over here is a plus. In fact, we see 1 and minus 1 are both inflection points because here is switches. Concave up on this side, concave down on this side, and then at 1 is concave down on this side, concave up on this side. So let's write our answer here. Inflection points are x is 1 and minus 1. And this is something that you might have been told if you learned something about the bell curve in a statistics class. We see it now with calculus. Here is the beautiful bell curve for the standard normal distribution. In terms of concavity, we see concave up, concave down, and concave up. And this means that x equals minus 1 and 1 are both
inflection points.
And now let me be a little more precise about what is exponential growth and decay. Certainly I've said those words when I sketched graphs of exponential functions, but this really means that the rate of change is proportional to the quantity at that time. So if we have A of t is the amount of some substance, or perhaps it's a population at time t, then exponential growth or decay, it says that the derivative, this is the rate of change, right, is proportional to the quantity. So this would be k times A. And I'll write another one. Typically, we have k is positive, and in this case, we have exponential growth because an amount of some substance or a population is always non-negative, and this would say the derivative is positive. Okay, so here, this case is growth, and in this case, this is decay, because we have the derivative is negative, is decreasing over time, and k is called either the growth constant or the decay constant. Okay, well, I'll just call this a note, and then we will check that A of t, when you have exponential growth or exponential decay, maybe I'll talk about growth first, it's the A0. A0 is the initial amount times e to the kt. This is for exponential growth. And this is an explicit formula. Now, let's just check this. How can I verify that, in fact, this satisfies this? Well, this here is what's called a differential equation, and we will touch on these more later. But to verify that this function, which is a constant times this exponential function, is a solution to this differential equation, all we need to do is take the derivative and see that we get k times the original function. Okay, well, this is chain rule. So dA dt is, that's a constant, and then we have derivative of the outside evaluated at the inside times derivative of the inside function. And then if we just move the k over here, we have exactly k times A, okay? So this, in fact, which I've been saying was exponential growth, well, it satisfies this in purple, that the rate of change is proportional to the quantity at that time. And similarly, this would be growth. If we write the decay, we get A of t is the initial amount e to the minus kt. And then again we can check dA dt is, well, chain rule. Derivative of the outside evaluated at the inside times derivative of the inside function, which is minus ka. Okay? Now, let's look at this example. On March 10th, 2020, the number of confirmed COVID-19 cases in the US hit 1,000. Okay, I was just reading about this online before recording to get some numbers to use. But at that time, experts claimed that the number infected was doubling every 4 days. And if you assume exponential growth, find a formula for the number of cases in the US T days past March 10th. So I am taking March 10th, 2020 to be t equals 0. Okay, I think it was maybe 2 days after that we went online for Northeastern. But in any case, okay? So we're assuming exponential growth, and I'll make a comment at the end about why we didn't actually see this function still today. Well, what do we know? We know a of t is the initial amount, t equals 0 is March 10th. It's 1,000 e to the k t. And then we know something that's also quite important for finding this formula. We know that this doubles every 4 days. At least at that time, people were saying that. Now, what do we need to have this formula? Well, we just need to find k, the growth constant, okay? So, doubling every 4 days means at t equals 4, we would have 2 times the initial amount, which is this. We would have 2,000 4 days later, okay? And now, well, divide, we get 2 is e to the 4k. Now, how can I solve for k here? Well, this is going to lead us into the next section, but it also really comes from last time we were talking about inverse function theorem, and I mentioned that the natural log of x is the inverse function for e to the x, and so we can take natural log of both sides. We get ln 2 is ln of e to the 4k, but because these are inverse functions, this is 4k. And so we know the growth constant is the natural log of 2 over 4, which is approximately 0.173. Okay? Now we can get this. It says that a of t equals 1,000 e to the 0.173 t. This would be the, this would be the number of cases in the US t days past March 10th. And just to connect this with the differential equation, we do have dA dt here. I'll put note. This would be, well, the growth constant times a. This is the differential equation here. Now, well, thankfully, due to social distancing and things like this, the number of cases in the US did not continue to grow exponentially throughout April, May, June, July, things like this. But this is a really great example of exponential growth coming from something very relevant and recent. Now, next time we will talk about the natural log function, the derivative of natural log, and do examples.